Okay, are there any questions from 5.1 or 5.2 or about the quiz in general? I saw no one this morning except for someone who's been away for like the past week. So I assume you guys are all good. Yes? So everyone should do really well on the quiz, seeing as I did not see you this morning. If you need to drop by after school, you can drop by after school. I can't stay for too long today, but yeah, and I will be here tomorrow during Flex. Okay? So today we are going to take a look at, in our fundamentals book, we are going to be on page 74. And this is going to show us how stuff dissolves. Okay, we're here. There we go. Okay, so anytime you need me to pause, just tell me to pause. I don't actually have a copy of the worksheet on me because I gave away my last one. I hadn't made quite enough. So just let me know if you want me to pause, if you need to write something down. Okay, just be like pause or like. Okay. He shouldn't have said atoms. What should he have said? Ions. Okay, so the ions come apart. What kind of a mixture is that? Homogeneous. So what kinds of bonds have been broken in the sugar molecule when it dissolves into the water? What kind of forces? Intermolecular forces are being broken. Okay. And actually, new intermolecular forces are being formed between the water and the sugar. Now, I think on your sheet, it gives different names to each of these processes, and they both start with the letter D. See if you can find them on your sheet. What do we call it when an ionic compound splits apart into the different ions? Dissociation. You guys should be familiar with the term to associate. Yes, if you associate with someone, you go and you meet with them. Yes, you get together with them. You associate. Well, dissociate is the opposite of that. It's when you move apart. Okay, so associate is coming together. Dissociate is coming apart. And what do we call it when the molecules separate from one another? Dispersion or dispersal, okay? Okay, now, I think we also do this one. Can you tell this is newer? He doesn't have like his cutouts, and his voice sounds better. His recording is a little better quality. But I do miss his cutouts, because the cutouts are just like so nice. You can see it's really complicated. Yes, we've got, what, 2 ring structures and some other bunches of stuff sticking off of it. Okay. You will never have to draw this in chemistry in grade 11 and 12. Maybe when you go and take organic chemistry, you might have to, or probably not even in organic chemistry. You'll probably just run across it in biochem. Okay, maybe you'll run across it in biology, but you wouldn't have to draw it. Okay, you would just have to recognize that, oh, look, that's a sugar. And when you study it, you'll be able to tell that. Carbon rings with an oxygen in them, sugars. Now, just before he starts talking again, we're going to take a look and we're going to say, okay, do you remember what charge the oxygen end of water is? Is it slightly positive or slightly negative, the oxygen end? Slightly negative. And the hydrogen end is slightly positive. So if we look here, we have a hydrogen end here, and the hydrogen in the sugar molecule is also going to be slightly, hydrogens are slightly positive. So we're going to have an intermolecular force in between that oxygen and that hydrogen. And here we've got a couple of hydrogens, slightly positive, are going to interact with that oxygen, slightly negative. So in essence, these water molecules are glomming onto that little sugar molecule and they're pulling it away from the other sugar molecules. Does that make sense? Cool.
Yeah.
Uh-oh. I'm plugged in, so no internet connection. Great, so much fun. I'm loving this. It's so awesome. Okay. Internet? No internet. Fantastic. Okay, so I guess we're not watching the video right this second. We'll have to come back to it later. Okay, but are you getting the general idea of how it works? Okay, and it works the same for the water molecules surrounding the ions. So let's now go back here and let's just check and see. We were working our way through page 67 last time. Okay, and let's take a look at page 67. So sad. So tell your partner what you remember about the word solubility. What is solubility? So solubility is the ability to dissolve. Did anyone try putting salt in oil yesterday? No one went home? Yeah? Did it work? It dissolved? Oh, it didn't dissolve. You saw that it didn't dissolve. Yeah. Okay, so some things will dissolve in one type of solvent and other things will dissolve in a different type of solvent. And actually, maybe because we're hanging out waiting for our video, we could take just a couple notes on that. Let's take a look at our ionic compound. Okay. We're not going to draw too many here because that gets tiring. And let's take a look at our water molecule. And even though these are only slightly positive and slightly negative, I'm still going to, well, I guess I could say this is slightly negative, and I'm just going to label these positive because these hydrogens positive. Will the water be able to draw the ions away from the other ions? I got one person saying no. Think about it, chat with your neighbor, see what you think. Does that help you, Tony? Will lots of water be able to lure the ions away from the other ions? Okay. We're not just talking one water molecule, we're talking lots of water molecules. What do you guys think? Does water have anything to offer those ions that they find attractive? Yeah, the water goes, or the ions go, oh, look, there's some lovely positive charges, and there's a whole bunch of them. And so eventually what'll happen is this negative ion will be surrounded by waters with all the hydrogen ends pointing towards the ions, or at least the negative ions. And of course, you would have is good? Okay. Could you draw a cation and draw what it would look like once it's dissolved in water? So hopefully what you've drawn looks something like this, where we have the cation surrounded by the slightly negative oxygen end of water. So that's why salt is soluble in water. Yes? Okay. What's something that doesn't dissolve in water? I will. Yeah. In fact, actually, I'm going to change the solvent first because it's easier to do that. Okay, so I'm going to go with oil and salt first, and then we'll look at water with something that won't dissolve. Okay, so oil. It's more complicated than this, but you can think of oil as just being a great big long carbon chain. Okay, because that's what it mostly is. There's a little bit more to it than that, but mostly oil is carbon atoms, and they are surrounded by hydrogens. There's a functional group in there or two, but we're not going to worry about those right now. It looks a lot like an alkane, okay? And for the purposes of what we're thinking about right now, this will do. I'll put quotes around it so you know that isn't really what oil looks like, but it's close enough. Now, does this molecule have a positive end and a negative end? In other words, is it a polar molecule? Polar means i.e. a polar molecule. Do you guys know what i.e. means? Almost. It means it stands for id est, which is the Latin. And id means that. Est means is. So in other words, that is to say, so i.e. means that is to say, or in other words, that's what i.e. means, is in other words. So if we have a polar end, if we have a positive end and a negative end, i.e., in other words, we have a polar molecule. So is this molecule a polar molecule or is it non-polar? Have a chit chat with your neighbors about that. Okay, now, is there anything different around the outside of this molecule? Are any of the areas on the outside different from one another? It's all hydrogens, okay? And hydrogen tends to be positive, although in this case, because it is attached to carbon, it doesn't even tend to be as positive. We'll talk more about that why later. Like oxygen is really good at pulling electrons towards itself and pulling them away from the hydrogen, whereas carbon is not nearly as good at pulling electrons towards itself. So the hydrogen here, you can just say it's all the same all the way around, so it can't have a positive end and a negative end because it's all the same. Yes? So we can look at it from that perspective right now. So this is, does it have a positive end and a negative end? Is it a polar molecule? The answer is no. Okay, so now let's assume, now instead of writing oil like this, what I'm going to do is I'm going to write oil. We're going to write the, the condensed structure. Did you guys have this in on the summer assignment? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Each of those little dots represents a carbon. Yes? And each of those lines represents a bond between the carbons. And we just ignore the hydrogens because it gets messy if we start throwing all the hydrogens on there. So this is a little representation of the oil. Okay, so this is our shortcut method of writing the oil. So let's take a look then at our ionic compound, salt. And what do we call this structure? Yes.
So for C, like for carbon the carbon balance, right? Does it have a covalent balance? or like is it overall?
I didn't understand that question. So does it have a covalent? What was the word after covalent?
Covalent bond.
Bond, yes, yes. Hydrogen and carbon are both nonmetals, so they have a covalent bond. Okay, so both nonmetals, so a covalent bond. Did that answer your question? Yeah? Cool. Okay. What do we call this structure? Obviously, it would be in 3D if I could draw 3D, but it's only in 2D. That is a crystal. What's the next word? Tell your partner. Lattice. And what do we call one of these units? That is a, tell your partner, formula unit. Now let's imagine that we now have some oil coming close to these ions. And oil is non-polar. No positive or negative end. Okay? Will the oil be able to lure the ions away from each other? Okay, and there's lots of oil molecules. Have a little chit chat about that. Decide what you think.
Oh, right. Same. All right. Then, it's not so much. Because the positive one is going actually, right? The sodium is still not all right. The ugly things like this, as it goes to the water, something like that. Water like this, but for oil, there's sure that you know, like, one of those
What do you think? I got one no. I got another no. I got some no's. Anyone want to say yes? No, we're not going against the tide. Even if we thought yes, we're like, oh, I'm too shy now because I don't want to like put myself out there. Well, yeah, let's take a look at this. These, the positive is attracted to the negative, yes? Negative attracts to the negative ion, and the positive ion attract. What kind of forces are those? Coulombic, yeah. Okay, electrostatic attraction. Did we talk about coulombic attraction yesterday? Okay, good. I just want to make sure because I've got the two blocks and I'm never sure what I did with which block. So they are attracted to each other. Now, let's say that this little positive ion here looks out at the oil, okay? It takes a little look. There's its little eyeball, okay? It's looking out at the oil, and it says, is that oil attractive to me? Or would I rather stay hanging out with these negatives nearby? Is there anything on the oil that is attractive to that ion? No. Okay? The oil has no positives or negatives to pull the ions away from their other ions. Okay? Okay? Because the coulombic attraction is stronger between the ions than it is between the ions and the oil.
What's the difference in the coulombic attraction and the IMF?
The coulombic attraction is responsible for all bonds and IMFs, all of them. Okay, so between two ions, that's an ionic bond, and that is caused by coulombic attraction. IMFs are also caused by the attraction between positive and negative, so those are also coulombic attractions.
Oh, so IMF is type of coulombic attraction.
Yes, IMFs are a type of coulombic attraction. Ionic bonds are a type of coulombic attraction. In fact, a covalent bond, if we look at a covalent bond, we have a nucleus and we have a nucleus. And let's say that this is a hydrogen molecule. Yes? In between those two nuclei, we have a pair of shared electrons. So what do we have here? We have positive charges next to negative charges, right? The electrons are negative. Yeah? The nucleus is positive. Okay, the nucleus is positive. The electrons are negative. And what does positive do to negative? There is an attraction between the negative shared electrons and the positive nuclei. So there is never a chemical bond without a positive attracting to a negative. There's never an IMF without a positive attracting to a negative. Yes?
So it's the covalent.
So the covalent bond, this here, those both together, that's the covalent bond.
It's also coulombic attraction.
It is also coulombic attraction. It's also electrostatic attraction. Okay, so coulombic attraction just means the attraction between positive and negative.
The IMF referring to the electrophile choose the forces between molecules.
Forces between molecules. But it's between positive areas of molecules and negative areas of molecules.
So your question is basically in general positive attraction negative.
Yes.
While IMF is just for molecules.
Yeah, IMF is a specific type of coulombic attraction. Ionic bonds are a specific type of coulombic attraction. Covalent bonds are a specific type of coulombic attraction. Coulombic attraction is
So if the forces of coulombic attraction within molecules are called IMF, so what's the force here? So the forces between the ions are also three.
Those are called ionic bonds.
Ionic what?
Ionic bonds.
Oh god.
Okay? So coulombic attraction is simply the attraction. BW means between. Okay, BW means between positive and negative charges. That's all that means. It's a big umbrella term. Everything that's positive that attracts to something that's negative, that is a coulombic attraction. So we could say to ourselves, in an ionic bond, what are the positive and negative things that attract? Ions. Cations and anions. Okay, I wanted to finish this sentence up here before I forget that we actually wrote it. So the coulombic attraction, when we had the oil with the water, is stronger between the ions than between the ions and the oil. Is good? Like ions are like positive, negative, yes, stick. If you want to think about it this way, you can imagine that the ions are like magnets. Yes? What do magnets do? They stick together. Now, imagine that you took a whole bunch of individual magnets and you threw them into a box. What would happen? They would all just, yes? What if you took some magnets, maybe some red magnets, and you took some blue magnets, but they're all just still magnets, they just have different colors, and you threw them into a box? What would happen? Yes? Are we imagining this? Doesn't matter what the color of the magnet is, as long as you've got magnets, they will stick to each other. Now, finally, let's imagine we've got all these separate magnets, and now we have some rocks. Okay? And I'm going to throw the rocks and the magnets into the box at the same time. What happens? Chat with your neighbor about that. Rocks and magnets into the box at the same time. And give it a little shake. And yes, you can give the little box a shake so everything can move around. It's a little fine. What's going to happen with the magnets? Come now, we just talked about what happens if you throw magnets into a box. What happens if you throw magnets into a box? Everybody, move your hands. Yes? They all come together. Yes? What will they do if there's rocks present? They will still come together, and if you shake it a little bit, the rock will be like, oh, and it'll get out of the way. Yes, because the magnets will kind of force it out of the way. So if you just give it a little shake, those forces are going to bring the magnets together. And what's going to happen to the rocks? The rocks are going to be excluded. They'll be on the sides. Yes? And that's exactly what's taking place here with our ionic compound and the oil. Instead of magnetic forces, we have electrostatic forces or coulombic attractions. Okay? So the ions stick together, just like those magnets stuck together. And the rocks, which had nothing to offer the magnets, they're like, we're not magnetic, we're just hanging out here. They get excluded. So the oil gets excluded. Does that kind of make sense? Because the oil's like, I got nothing to offer you. Now, if instead of the oil, we had different magnets, we could give it a good shake. We could smack it around a little bit and separate things, and the red magnets would work their way in between the blue magnets. And that's what's happening when you have water and the ions, because water has something attractive. If you give it a shake, or if you heat it up, or sometimes if it's very soluble, you won't even need that. You just let it sit and it will dissolve. Is good? Okay. So when you're thinking about these things, just think about magnets and rocks. Yes? And if anybody wants a printout of this, just let me know at the end of class and I can print out all these notes. Okay? So if you're like, wow, everything just kind of got crazy. Okay. So we said the coulombic attraction is stronger between the ions. And remember, the ions are like magnets. Than between the ions, the magnets, and the oil, which is like the rocks. Yes.
So for oil, right? So it is between carbon and hydrogen.
Yeah.
How do we know how much hydrogen we have?
How do I know how many hydrogens are on there? Yeah. So what I would do is I would look at every carbon and I would say carbon needs to have 4 bonds. Yes? So I have my string of carbons and that takes care of 2 bonds for this carbon here. Yes? So I would need to have 2 hydrogens on that carbon to fill up the other 2 spaces.
Yeah.
Yeah?
So what could it be like 1 carbon and 4 hydrogen?
1 carbon and 4 hydrogen, you absolutely can. Okay? So you would have 1 carbon and 4 hydrogen. That's just a different molecule. That's methane. Yeah? So you could have 2 carbons and you would just, instead of having all of this stuff here, you would stick a hydrogen on the end instead if you just wanted 2 carbons. Yeah? Okay. Okay, so will the oil be able to lure the ions away from each other? No, because the oil has no positive or negative charges to pull the ions away from the other ions. And now going back to just sort of talking about coulombic forces in general, and we did not label this guy here. This whole thing this is the covalent bond. It is the attraction between the shared electrons and the positive nuclei. That's really ugly. There's too many arrows there. I'm going to get rid of that. And I'm just going to write covalent bond here. Covalent bond. There we go. That's better. So we have coulombic attraction, the attraction between positive and negative. In an ionic bond, what are the positive and negative things? The cations and the anions. In a covalent bond, what are the positive and negative things? Chat with your neighbor about that.
It's just
I feel like I'm saying the same thing over and over here, but that's okay. In a covalent bond, what are the positive and negative things? You guys chose to be an enriched. You should be like, yes, ask me. I'm happy to give you an answer. I will tell you something. There is a concept called intellectual risk-taking, okay? This is not like risk-taking, like, oh my God, I saw a video the other day and it was all these crazy things that people did. They were like jumping, this man jumped off a building, like, I swear to God, like 10 feet from the building, there was a lamp post, right? Like this is like a 2-story building. The lamppost was really tall. He jumps off the building, grabs onto the lamppost and slides down. I'm like, ah! Okay. There's this other guy, he like jumps off this huge tower and does this like spin and lands in the water. And I'm like, ah! That's not the kind of risk-taking I'm talking about here. The kind of risk-taking I'm talking about is saying what your ideas are. Okay? And you might be wrong. And Joanne, before I get to you, I'm just going to tell you guys a little story about a student many years ago named Allison. And Allison was a student, one of my first students in Chemistry 11 Enriched and Chemistry 12 AP. And Allison would answer most of my questions. Every time I asked a question, Allison, ooh. And you know what happened every time Allison answered a question? It was wrong. She answered it wrong. Like, so consistently, we would laugh about it, right? Because she was like, oh yeah, it's wrong again, whatever, ha 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 ha. Do you know what score she got on the AP exam? It's out of 5. You can either get a 1, which is low, or a 5, which is high. Do you know what score she got on the AP exam? 5. She got a 5. Do you know why? She got all of her misconceptions out during class, right? So she had none left by the time she got to the exam, okay? So I will encourage you to be an intellectual risk taker, and I guess we're heading outside. Goody.